那你不得开心吗？那你找老婆就可以不开心了。你啥意思？
All right. So why don't you guys take these first few minutes and see how much you remember about binary search trees. See if you can write a function that takes a binary search tree of numbers as defined in the course notes, and write a function that produces a list of all of the numbers that are less than n. So we're going to consume two arguments and produce a list of numbers less than n. And that's strictly less than, so no equal. Oh. Put that back there. All right, so you've had a couple minutes to think about this little function here. So let's just talk about it before we actually write the code. So first off, remember that a binary search tree is special. First off, it's obviously a binary tree where internal nodes have at most 2 children, but also remember that everything in the left subtree is going to be smaller than the current node, and everything in the right subtree is going to be bigger than the current node. And we can take advantage of that particular fact to reduce the search space for this particular problem. So first off, if n, the thing we are trying to find numbers less than, well, if is smaller than the current node's value, then there's absolutely no reason for you to search for anything in the right subtree, because you know that if n is smaller than the current node, the only place it could possibly be is down the left subtree. However, if the current node's value is smaller than n, so I think I meant bigger in the previous one and smaller in this one. So if it's smaller than n, then numbers exist down the left subtree. But since the current node is smaller than n, then there may also be nodes that are smaller than n down the right subtree. So you're going to, in the case where the current node's value is less than n, you actually have to visit both left and right subtrees. So let's actually write the code. Let's go over to Racket here. Let's bring open a tab. And I've already got the node structure in here. And I've got my prototype for the function, and I've got a test tree. And so now what I need to do is fill in this function. Now, base case. Well, the base case is the binary search tree is empty, in which case the item doesn't exist. And in this case, since we're trying to produce a list of values that are less than n, we're producing a list, so our base case should produce empty. Now, there are two cases. One where n is less than the current node's value, and one where n is bigger than the current node's value. So let's do one where we say, let's do n is less than the key of this node. This is the case, so for n is less than the current node's key, well then I know that there's no reason to look down my right subtree because n is smaller than me. Okay, so in this case, we are only going to search for items less than n down our left subtree. So we're going to produce simply now you note there's no cons in here. We're not doing anything with the current node because the current node is bigger than n or equal to n, which means I don't want it. So I'm just going to produce the list I get from searching for items less than in the left subtree. Otherwise, this is the case where n is actually bigger than the current node's value. So otherwise, what I'm going to do is I need to go down the left subtree looking for things, and I need to go down the right subtree. And since the current node's value is less than n, I need to keep it, which means I'm going to need to add, I can spell, the current node's value to the list that I get from searching for things down my left subtree and searching for things down my right subtree. Now, I'm going to get a list of things from my left subtree and a list of things from my right subtree, and I want this to produce a nice flat list. So the function that I want to use to combine the results of searching the left and right subtrees is actually append. So I'm going to append the results of searching for the key, things less than n, down the left and down the right. Make sure I got all the brackets. Why would I want to do that? There we go. So we have a test tree down here, test 1. And if we were to actually draw this tree out, we got 5. And I usually put a 3 here. 7, 6, 9. So there's our tree. So I want to produce the list of all the items in this tree that are less than 10. You and I both know from looking at this tree that we should get a list of all of the elements in the tree. And there we do. 5, 3, 1, 4, 7, 6, 9. We get them all. Now, I want to produce a list of all of the nodes in the tree that are less than 0. Well, all of these nodes are bigger than 0, so this should give us an empty list. And we get our empty list. Now, what about things that are less than 5? We should get 3, 1, and 4, but not 5, because 5 is not less than 5. 5 is equal to 5, and we only want things that are less than n. T is not 5. Now, what went wrong here? Just a minute. I got these cases backwards. The problem here, by the way, is by putting these cases backwards, I ended up with nodes that are equal to n being added to the list. So let's fix that. Everybody makes mistakes in code. It's really important that you can see the result and figure out what went wrong. So what I'm going to do is I'm going to change this just a little bit. We are going to say if I'll take out a case there. Now when I run it, there we go. This points out two things. It's really important you know how to debug your results, but also it really makes a point of saying make sure you're putting your conditions in the right order. It's easy to think you can flip the order and you can't always. So there you go. Now what? Any questions about this one? All right then. If you have a clicker, please get it out. I'll give you a minute for each of these. Yep. No. Because we said internal node, which means it has to have at least one child. Yeah, but not includes 0.
This is the problem with conventions.
I know. All right. If you haven't clicked it, please do so now. And let's see where everybody fell. Everybody said the right answer. Yeah, it's B. All right. So if internal nodes have just 1 or 2 children, that's a binary tree, not a general tree. I mean, binary tree is a kind of general tree, but it's a very specific type of tree. Leaves can't have children. That would be like going outside and like you see a maple leaf with like branches coming out of it. That's weird. I'm not saying it's never happened. That would be very weird to see. And there is more than one root. No, that's not a tree. So indeed, internal nodes can have any number of children. And by any number of children, we mean one or more, where more is as many as you want. All right. Let's see if you can keep your perfect record with the next two, right? It's like pressure's on. Can you get 100% on this one? All right. There's one person who hasn't pushed a button. You have 10 seconds to do so. All right. I'm going to stop it now anyways. The answer is... Okay, that's funny. A tree can be represented by a list. Yes, it can. Because if you actually look how we could implement a defined struct, or structures in general, we could just do it as lists. We can represent anything with a list if we really wanted to. All right, you rebels. I got a good idea as to who you are. All right. This one is harder. If you're having a hard time thinking about this one, insert the elements into a binary search tree from a sorted list. All right, come on, there's like a few of you who haven't pushed something. All right. I see the mystery missing person now. Push a button. Okay. So let's see what everybody said. Ooh. The answer is A. Here's why. A binary search tree is a binary tree which simply says that internal nodes have at most 2 children. No other restrictions. And a binary search tree is a binary tree where everything in the left subtree is smaller than the current node and everything in the right subtree is bigger than the current node. The binary search tree and binary tree definitions say absolutely nothing about whether a tree has to be balanced or not. And balance is in reference to how does the height of the left subtree compare to the height of the right subtree. There's no rules about balance in a binary search tree. If you take a sorted list of numbers and you insert them into an empty binary search tree, one after the other, a sorted list goes in and a sorted list comes out. You end up with a tree that looks like a list. Which means that the worst case binary search tree is height n. Roger is so excitedly nodding his head yes because he wrote an exam all about it. All right. So then, some things you would probably like to know is that your midterms are all graded. They finished grading on Tuesday night. And then I had to have one of the questions regraded because it wasn't up to my standards. Roger was ever so kind as to regrade it. You should all thank him because it resulted in you guys getting more marks. Now the average, if we include all of the people who didn't show up, the average is 75. If we get rid of those people, which we do when it comes to computing averages, your average is over 81. So, and your grades, by the way, should be coming out very, very shortly. So you had absolutely nothing to fear or panic about the last few days. Just to give you an idea, there's the spread. It's very, very high, which is lovely. Yep. So that's the tradition, right? If you have a final with a high average, you know you're going to get pillaged on the final, and vice versa. I think that's horrible. Your final is going to be as hard as the final was always going to be. It's going to cover all of the content of the course, and I'm not going to put a problem on there that's impossible to solve. That being said, it's very easy going into the final exam thinking, hey, I got like 90 on the midterm. That means I don't have to study for the final. You have to study for the final. Keep in mind that the final is going to be much heavier on the post-midterm content than the pre-midterm content. And I'd like to point out that the post-midterm content is significantly more difficult than the pre-midterm content. So it's not that I'm going to go out and make an on-purpose exam that's like putting you through a juice machine. No. I'm going to make the exam the same way I always have. Now, for the record, it's already like half written, so that's fine. But you still don't get a false sense of hope from a high midterm. Yeah. I'm not complaining about an 81 midterm average. It's great, right? In terms of difficulty of the midterm, I was aiming to have the difficulty somewhere between the traditional midterm 1 and midterm 2, because if you take this in the fall term, you get that practice midterm, which is known as midterm 1, that gives you the idea of what does a CS midterm look like. And then, you know what to do for the second midterm. You guys didn't get that practicey midterm, so I tried to make the difficulty level balance out. I think you guys just studied really hard, to be honest. There's a few things that are different between this term and previous terms. You have recorded lectures that you can review whenever you want. That's a study material. And I know that the younger generations do tend to watch YouTube to learn things instead of read books. Part of why we do this. For me, learning to code from a YouTube video is a very weird thing. But that's because I learned to write code before there was internet in your home. So fair enough there. But I mean, we've been doing a lot more debugging problems on assignments, which really help you understand code. So I don't think this was us giving you an easy midterm. I think you guys just studied hard and you did well, and that's great, and I'm happy. So it sucks to be one of those 10 people that was sick. That being said, if you were one of those 10 individuals who were not able to show up to the midterm because you were sick or whatever, if you have not already submitted a VIF, that's a verification of illness form, please do so as soon as possible. They're really easy to get. You show up at a clinic and you say, I'm sick, and most of the time they hand you one. Although some clinics make you pay for them. Yeah, all right. That being said, please don't commit VIF fraud, because if you do and we find out about it, then you know how, I don't know if you know this, the university like several years later releases all of the academic offenses as this lovely PDF, no names attached, but everybody likes to go through and find all the silly ones. There's always some that are really funny. When I first started being a grad student and TAing things, somebody actually got an academic offense for showing up to the pack in a chicken costume.
I saw that video.
I think there's a video of it. That was pretty funny. I thought that was hilarious, but apparently the school did not think so because that's a distraction to the others writing the exam. I was once tempted to show up. I once made a bet with the class, or I wanted to make a bet with the class saying, I will show up in cosplay to the final exam if you guys beat everybody on the midterm. But after that incident, I was like, I can't do that. So, although, try to give me an academic offense. I'm not a student anymore. At the time, though, that I was thinking of making that bet, I was, though. So, yeah. Anyways. All right. So your midterm grades should be released to you very shortly if they have not already done so. My estimate is that it was happening sometime during this lecture. We are also releasing to you post-mortem, so what were common mistakes, and we're also releasing the solutions. They'll be posted, I think, to Piazza, if memory serves me. And then if you have the desire to have your stuff remarked, there will be instructions posted. The remark system is not up yet and running, but I don't like accepting remarks in the first 24 hours anyways because you haven't had enough time to think about things. There will be a time limit on remarks. All right, any other questions about that? Everybody feels relaxed now? All right. Well then, we don't want to go there. We want to go over here. So just to review where we were at the end of last class, we were talking about nested lists. And remember, we've just mentioned, that you can represent a tree as a list because you can represent any structure as a list. You just say, okay, this field is this element of the list, and so on and so forth. So we can actually take a nested list, and what's interesting is we can actually draw it as a tree. And you can take any tree and you can likewise draw it as a list. And then to do some stuff with nested lists, we give you a data definition, which has 3 parts. A nested list was either empty or consing a number onto a nested list of numbers. So that would be like the flat level. And then, or it is consing a nested list onto another nested list, which would actually have 2 lists inside of one list, which is cool. And then, of course, because we've created this data definition, you might be thinking, oh, we can only have nested list of numbers. No, you can have a nested list of whatever you want. So we could have a nested list of anything. That's totally fine. The template for that looks like so. So if the list is empty, you're going to do something. If, however, the first element of the list is an atom, so like, or a simple thing like a string or a Boolean or a number, anything other than a list, then we're going to do something with that first element of the list and relate it in some way to the rest, computing the template of the rest of the list. If, however, the first item of the list is in itself a list, then we're going to relate the results of calling the template on the first of the list to the results we get from computing this template of the rest of the list. So that's our beautiful template there. And then we can use this template to do a variety of functions on nested lists, like counting how many items are in the list. And by items, we're not referring to how many lists are in the list. We're actually referring to how many things like numbers, strings, and so on are in this list. And the thing to point out there is if the first item of the list is an item, or like a number, then we want to add 1 to the count. And if it is not an item and it is a list, then we want to add 0 to the results of counting the number of items in the first list and in the rest of the list. So in the case where it's empty, we produce the base value of 0. In the case where the first item is not a list, we add 1 to the count of the number of items in the rest of the list. And in the case where both the first item is a list, we're going to add the results of counting the items in that first list to the results of items we get in the rest of the list. That will actually, this is traversing a tree. It's visiting every node in the list. Now, there is a trace on the next slide. I really don't like going over the traces that are in the notes because that's me just talking at you for something you can just read. I don't really find that useful. So I recommend for you, if you're struggling to see what's going on with this particular function, to trace through this code yourself. There is nothing more valuable when it actually comes to developing code than to actually tracing it yourself. You will never learn an algorithm better than when you actually do it yourself. So, trace through that yourself. The next thing we did was flattening a list. And again, we covered this very briefly last class. And flattening a list is, we want to take it from this nested thing into something where all of the items are actually at the top level. That is, it's just a list 1, 2, 3, 4, 5, 6, 7. So in order to flatten the list, well, if the list is empty, I produce empty. So because I'm going to produce a new list. And if the first item of the list is just an item, i.e. it's not a list, then I want to cons that item onto the flattened rest of the list. The tricky part is, what do you do when the first item is itself a list? Well, you're going to want to flatten that first list, and then you need to flatten the rest of the list, but then you've got to combine those two flattened lists together in some way. And it's tempting to cons it, but don't cons it, because that's just going to produce another nested list. If you want to append two lists together, you use append. Yeah.
So why do we like to use append?
Well, if you're looking for a particular challenge, implement flatten without append or your own implementation of append. That's a fun one. Here's the solution anyways. It's fairly simple. Again, base case empty. In the case where the first of the list is an item and not a list, we just cons that item onto the flattened rest of the list. Otherwise, if the first item is a list, we are going to append the flattened first list onto the flattened rest list. Good. Nice flat list. Which we like flat lists. All right. And again, on the next slide, there's actually a trace of this function. I'm not going to trace through this. I really recommend you do that yourself. So, I want to do a sample problem here, but before we do one more sample problem with nested lists, I want to show you something. So I keep saying trace through things yourself. So I've been working on assignment 8 for you, because I decided I don't want to reuse an old assignment 8. I want to make a new one. It's going to be fun, right? I think it's going to be fun. You're going to implement autocomplete. It'll be great. So, I don't know if it was because it was 3 a.m. or because I wanted the algorithm to work out in a specific way, but when I started writing code, I got the wrong answer, so I was like, you know what? That's not how you write code. How you write code is you think about the problem you're trying to solve and you work it out on a piece of paper before you ever touch the program. So these are actually my notes for creating the solution to the bonus problem for assignment 8. I actually drew out some trees and traced out some pseudocode until I got the answer that I was looking for. I actually traced this all out on paper before I ended up writing the code. So if you think this is just something I'm telling you and I don't actually practice myself, actually that's not the case. These are my own personal notes from tracing through one of your bonus problems. This is something, by the way, I do with all code that I write. I work it out on paper first. So it used to be I always did it on paper. And then we actually had like stacks of ridiculous amounts of paper lying all over our house. And so I ended up getting a tablet and then doing it on the tablet. But now my daughter's taking the tablet, so now. And I can't find the pen to that one. So I'm back to using paper. I have probably thousands of pages of notes that I have made planning problems out before I ever touch the code. So this isn't just advice that I'm giving you and not practicing myself. This is something I actually do. I mean, if you don't believe me, you can come and read what's actually written on this if you really want. It's not very legible, but. So that being said, I want to solve another problem on a nested list. what I want to do on a nested list is I want to determine if an item exists in the nested list. But instead of doing just a nested list of numbers, I want to do a nested list of anything. And I want not to just be able to search for an atom in the list. I even want to be able to identify if there is lists contained in that list. So I'll show you the solution. This one isn't actually that hard, by the way. There's my solution. So first off, I'm kind of making the requirement that whatever it is I'm searching for in the list has to be non-empty. So I'm not permitting myself to search for empty things. That doesn't make sense. So what I'm going to do, otherwise, is I need to determine if this item exists in the list, but the item can be of any type. So one of the first things I know is that because the item can have any type, I can't use equal, the operator. I can't use char equal or string equal. The only operator for comparison that will actually work, given that the list can contain anything, and I'm permitting the search for anything, is actually using equal question mark, even though it's not terribly efficient. All right, so base case, the list is empty, doesn't exist, produce false. The next case is the current item, the first item of the list, equal to the thing I'm searching for? If it is, produce true. Now you will note here, I did not check if the first of the list was a list, because I'm not restricting the user from searching for lists inside of this list. I will give you a demo of that in a minute. So I've got my base case for the list is empty. I've got a base case for the current item is the thing I'm looking for. That leaves me with two cases left. The first of those cases is what if the first item of the list is actually a list? I need to search through that list to see if the item exists. But the item may not exist in the first of the list, so I may also have to search the rest of the list to see if it's there. So if I have to search both the first and the rest, I need to combine those results together in some way. Now, if I want to know for the existence of something, I just want to know if at least one element in this list is equal to that. So the best way to combine the results from the first and the rest is using an OR. One true, the whole statement produces true. Now, in the case where the first element of the list is not a list, then I just need to produce the result of finding the item in the rest of the list. Because the current item is in it, and it's not a list, so I don't need to search it. I just need to search the rest. Yeah?
Would it matter if instead of cons predicate we use list predicate? Because technically we are testing for empty in the first case.
You could.
It wouldn't matter.
It wouldn't matter. It has no impact on it because you're right. You well, actually, no. So this is saying, no, it doesn't matter. I mean, there would be one extra recursive call, but it would immediately go to the base case because the first list might actually be empty. So you would end up calling find on an empty list, which would produce false, which would be fine because you'd OR that in with searching everything else. But it's one extra recursive call, so you want to reduce the number of calls, right? All right, so let's test this out. I've got two nested lists down there. Yes, they're all numbers, but that's okay. I'm just going to clear that out. So then, let's try to find in test one. Oh, what order do I have these parameters in? Find item. So let's try to find 2 in test 1. It exists, so of course we get the expected results. And we should also be able to find 2 in test 2. Now let's search for something that's not here. Let's search for the number 87. We get false, which is what we anticipate. Now this is where things get interesting. You should be able to search for anything, which means you should be able to search for a list, a non-empty list. So let's try to find 4, 5, 6 in test 1. And it produces true. So it's kind of a fun one. All right, any questions about this implementation? So part of the reason why I was showing you my own notes here for actually solving a particular problem wasn't so much for this example here, because this one isn't so bad, but I was showing you that I actually worked this stuff out on paper because assignment 6, how many of you have actually started it? So it's kind of a shorter assignment, there's fewer questions, right? But you might have noticed that those questions are a little bit harder. And a little longer, yes.
It's only one question, but it's
All right, so some of those problems that we've asked you to do may require a lot of little helper functions. And it can be very difficult if you just sit there and start writing code to actually get the correct answer or to realize what all helpers you need. And if you did what I do and you actually work it out on paper, then when you actually sit down to write the code, you already have a complete plan for what you need to do. You don't need to figure anything out because you've already figured it out. And by the way, a hint I will give about assignment 6 is there's one function on there. I think it's like the one where you compute the winner between 2 cards. And many of you are going to be ever so tempted to use recursion to compute the winner between 2 cards. You don't need recursion. There's a simple math formula you can use to compute the winner. I won't tell you what it is, but I bet if you sit down with paper, you can figure it out. Yep. No, you will not be penalized for using recursion. And I think I even listed it in the assignment guide that you don't technically need recursion for this. You can, if that's the only solution that you have, that's okay. And that's one of the things about programming, is sometimes it's better to have an answer that works than the answer that's most efficient. Yep. I didn't use recursion for that. All right. So with that, then, by the way, we are actually done Module 11, and we are ready to move on to lovely, lovely Module 12. All right. So I'm going to jump around in these slides a little bit because I'm going to jump around in them a little bit. So we're going to start on slide 3. So you've been writing scheme bracket code for like 2 months now. And with that, we've always told you you need to write constants whenever you have something like C or the gravitational constant or pi, or maybe the value of a quarter, you should make a constant for that. And we've also told you things like, hey, if you see blocks of repeated code, you should write a helper function for that. Or if you were doing a cumulative recursion, you by necessity needed to have a wrapper so as not to expose the accumulator to the user. Okay. All right. So let's then take all of that programming skills you've got from 2 months of bracket, and let's look at this function here. So this is called Heron's formula, and this is a formula that takes a triangle and computes its area. So it takes the side lengths as A, B, and C, and then it takes the area as the square root of S times S minus A times S minus B times S minus C. And what's interesting is S in itself is also A plus B plus C over 2. Okay, if I asked you to translate that into rapid, you should all be able to do that. I mean, it was kind of on your midterm question 1, but there it is, translation. And it works. And technically speaking, there's absolutely nothing wrong with this. It is a direct translation. I don't like it. I don't like it because S, which is equal to A plus B plus C over 2, we've repeated the calculation of that. There's 4 copies of it. That's silly. That's goofy. So there's 2 ways that you could solve this. One of the ways is you could be like, I know, I'll go to Heron's formula, and I will make note of the fact that if S is A plus B plus C over 2, and I compute S minus A, then that's actually equal to negative A plus B plus C over 2. And I'll do that for B, So S minus B is A minus B plus C over 2. And for C, S minus C is A plus B minus C over 2. So I could go through and I could change that and get this version of the function. But when I look at this function, I'm like, what the hell is this? I don't know what this is. All that rearranging, if I were to look at this and try to debug this, I would be like, what the hell is this person doing here? And I'd have to get out the formula, and I have to, oh, I see what they've done. They've rearranged everything. Oh, that's kind of sad. When you write code, you should be writing code that is striving to be as readable as possible. That's not just about comments. That's not just about identifier names. That's also about, does the code actually read like the function it's supposed to be implementing? This doesn't. So let's not do that. Now, you're probably all sitting there like, the obvious answer is to write a helper function to compute S. And then call S. So here we've done that. So I've called S, created S, A plus B plus C divided by 2. And then inside of parent's function, I multiply the result of calling S, A, B, C, S. You know, we externalized or abstracted the computation of S in a helper, but I still call it 4 times. What's up with that? And now it looks kind of weird because now I have SABC because I gave it a terrible, terrible name. But what other name was I supposed to give it because it's supposed to compute the value for S? Here's another way you could phrase it. We notice the fact that we need the value of S 4 times. So instead of making the computation of the value S a helper function, what if instead I have S be a parameter to the helper? So I compute S once and pass it into the helper. So that's what I have here. I have this helper function, and it takes 4 arguments, A, B, C, and S. And S is pre-computed. And then inside you'll see square root of S times S minus A times S minus B times S minus C. Wait a minute. The body of that function looks exactly like the formula we're trying to solve. Very readable. And then the wrapper for it simply passes in A, B, and C and the computation for S. It's beautiful, isn't it? It's 4 lines of code. And 20 lines of design recipe. Or more. Well, I don't like this either, actually. Here's the problem. These 2 functions exist at what we call the top level. That means I open up my Racket file and I put the definition right there. What that means is that these 2 functions have what we call global scope. They are visible and accessible to everything inside of that program or that file. Do I really want my user to have access to this helper function? This helper function requires that we've pre-computed S. It was really just meant for us to use to simplify the implementation of this particular formula. But because of the way Racket works, this particular function is provided at the top level, which means that the user actually has access to it. And a dark and deep secret about accumulative recursion is, you know how you have that accumulative recursive function that you didn't want the user to be able to use because you don't trust them to pass the correct initial accumulator value to, so you wrapped it? Well, that accumulator function is also living at top level, which means technically speaking, the user can call it and use it incorrectly, and then you're going to get an angry phone call that says, hey, this doesn't work, except they've used the wrong thing. It's a lot of the time, many of the constants or many of the helper functions that we create really only make sense in the context of the function they were created for. And exposing them at the global level exposes stuff to a user or a fellow developer that maybe we don't want them to have access to or know about. So what I'd like to do is I'd like to be able to take all of those helper functions and constants and push them inside of the function they're supposed to be helping so they are not exposed at a global scope, so nobody can see them. They're hidden. And if you're sitting there thinking, well, you can't do that in Racket, actually you can. So this is how we would do it. We're going to use this local syntax. What local does is it lets us define a bunch of things and then use them in some expression. So I am going to take, and I'm going to rearrange this function a little bit. So I have a local inside of this function, and it has a list of definitions. And I'm going to define S to be A plus B plus C divided by 2. And then in the body, I can just use that computed value of S. And you'll note here, I have no helper functions that live outside. No constants that live outside. Everything is inside the function. And so the user will only see this triangle area function, and they won't see anything else. So they don't have the opportunity to call functions that they probably shouldn't have been allowed to call. This is pretty cool, by the way. So local is a special form, by the way. And now I'm going to jump back up to slide 2 to show you the syntax of local. So you have local, and it takes 2 parts. The first part is a list of definitions, and the second part, so there's your list of definitions, and the second part is the body of the local. It's an expression. Now here's some rules. The things that you defined in this local can only be used in this body expression. They do not exist outside the local. All right. So that's a very interesting thing, by the way. Yep. Yes, you are. In fact, you can put a local anywhere. We'll get there. You require a subset of the design list. So this gentleman over here asked, can we have nested locals? And I respond, you can have them anywhere. Let me show you. So let's do this. Let's clear it up. Oh, wait. All right. Let's add some numbers together, right? Well, maybe let's add some locals. I gotta make sure I get all the brackets right. There we go. I have a local being used as an argument to add, and inside the local I have another nested local. And it works. That's fun, isn't it? So you can have a local as a question in a cond, and you can have a local as the answer in a cond, and you can have a local as an argument. You can have a local anywhere where an expression needs to go. I feel like I'm reciting a Dr. Seuss book right now. I think it's Green Eggs and Ham, actually. Locals can go anywhere. Now, just because you can put them anywhere and nest them as much as you want, that doesn't mean you should do it. It's one of those things. Racket lets you do a lot of things, but that doesn't mean you should. The problem with writing code like this is somebody's going to sit there and look at it and be like, what in the hell is going on here? So while it can be done, please be careful with them. Yeah. Let's do it. So this individual up here has asked, what happens if in the second local I redefine x? What happens? By show of hands, how many of you say this is going to cause an error? How many of you say it's not going to be a problem at all? The answer, by the way, is it's not a problem at all. So, x is now 15, and let's do x plus x, and is no problem. None at all. All right, so what's going on here? Yep.
Is it because the dx is defined only to the body of that local, not to the other?
Yes. The word you're actually looking for is called scope. And scope is a big thing in computer science. It's something you have to pay very close attention to. So what I want to do is I'm going to go over to one of my files I've already done here. I'm actually going to erase everything below here and start again. All right, so I have this function magic. And I have a definition for a constant named item. Item and magic are both defined at what is the top level. Global scope. You cannot have multiple definitions in the same scope for the same name. So I cannot redefine item in this scope. So if I actually uncomment this line here, where after I define item as a constant, I then define item as a function taking 2 arguments, bracket's going to say to me, whenever it gets off its lazy button runs, that item was previously defined. Yes, that's exactly what Oak was doing, but what's interesting is even the body of a function is its own scope. So let's actually draw this out. So we can't do this, but you may notice here that the function magic takes an argument item, and it uses it inside the body of that function. Well, item, the argument, is defined for the scope of the function's body. It was not defined at the top level, it's defined within the function's body. So that's okay, because we have definitions at different scope levels. And the meaning of a value, of some kind of identifier or constant or function, is always going to be the one at the most accurate scope. So inside the body of the function, we'll use the definitions for the inside the body of the function. And if they don't exist inside the body of the function, but they exist in the global scope, then we'll use the global scope ones. Now, what complicates this even more is that inside the body of magic, I defined item again. So, when I actually add item to my argument to m, which value of item is actually going to be used here? There are 3 possibilities. There's the global one, there is the argument, and there's also the one in the local definition. Which one is used here? How many of you say local by show of hands? Anyone disagree? Oh, it is the local, because that is the most precise scope. So to draw out scope, I actually like to, and I mean this is one of the advantages of a language like C that uses the curly braces to encompass scope blocks. So let's rewrite some scheme code as C or something. So we have the top level global scope. Oops, that is not how you spell scope. I can write programs, but don't ask me to spell things. All right. When we usually have scope, it is tradition as you go inside of another scope, you keep indenting. So if you ever wonder why my indentation looks a little odd in bracket, it's because I'm using scope indentation. All right. So at the top level, I have a define for item, and I have a define for magic. And this is the body of magic scope. I'm sorry, I write so much C and C++ code that if you're wondering why I just put 2 slashes, that's comments. All right. So, inside the body of magic, well, item was an argument, so it is defined inside the body of magic. And then inside of the function magic, we have a local, which is yet another scope. And inside there, we've defined item to be 8. And we also have defined m to be something, see, 10. And then that body expression for the local exists, that's the local scope. That's what we do within the local scope. So now, this is where we are adding item and m together. We are always going to use the definition to the current scope. So item exists at all 3 levels and has 3 different meanings. But in this scope, we will use this scope's definition of that thing. Now, let's suppose there was no definition of item in the local scope. So maybe it was, oh, that's technically a valid name, so here we go. So item does not exist in the local scope, but that's not an error, because it exists at the scope above you. If an item is defined at an upper level of scope, then in the inner one it can be used. So anything defined at the global level can be used anywhere. Arguments can be used anywhere inside the body of the function. Defined things in a local can be used anywhere in the body of that. But it's not the opposite. If you define something in a local, you can't use it outside. If you have an argument to a function, that argument name is not usable outside the body of the function. Any questions about the scopy stuff? It gets tricky because we like to ask you these trick questions where we've defined something like this, where item exists at all 3 levels of scope. And then we ask you, hey, what's the value of this function? And you might be thinking this is how people write code. If I hire you and you write code where you've redefined the same named thing at 18 different scopes, I will fire you. Because that is not readable. Yes, any intelligent developer can look at this and know what value of item to use. But the problem is not everybody understands scope very well. You want to strive to make your code as readable as possible. You must assume when you are writing code that your fellow developers are idiots. So you must make the code as easy to read as possible. But not just for them. If you go away from this code for 2 weeks and come back later, you don't want to have to figure it all out again. So just because you can redefine something at different scopes doesn't mean you should. Just because you can use a local wherever you want doesn't mean you should either. But it is powerful and you can do it if you want. And if you're wondering, can you do this in other languages? Yes, you can. Some languages are even a lot more permissible than others. For example, in C++, I can have multiple functions with the same name, but so long as their arguments and return types are different, they're technically different things. That's kind of fun. Can't do that in Mac. All right. So now you've seen local, And you've kind of got the idea that this is going to let us take our helper functions and constants and stuff them inside the function that they were helping, which is pretty cool. But, of course, now we run up against the problem of we're going to ask you to step through this code. Trace the steps. Give us the substitutions. So how do you do that with the local? Yeah, there's a little extra work involved. So, first off, we have the problem that the names of things inside the local, all of the things we define inside the local, their names may actually clash with things at higher level scopes. So what we're going to need to do is before we can actually, trace through the code, we are going to rename all of the things that are defined inside the local. We're going to give them a unique name that couldn't possibly be used anywhere else. Then what we're going to do is we want to get rid of the local. That's really what we want to do. So what we're going to do is after we have renamed each of our defined things, I'm going to replace all of the places where those old names were used with the new names. And then to get rid of the local, I take all of the defines and I lift them out of the local. They're now at the global scope. And what's cool about this is because we changed the names to something unique, I know that it won't clash with anything in the global scope. Then I drop the local and replace it with its body. So here are the formal steps for it, and then we'll do an example. So in one substitution step, all of the stuff on this slide is going to happen, and it's a lot. One step. The first thing that you have to do is replace each of the identifiers, that's the names, with a unique name. Not only in the defines, but anywhere where those were used, you're going to replace them with a new name. Usually we do the old name underscore a number, and then maybe do underscore new, or it doesn't matter, something unique. And then what we're going to do, in the same substitution step, after we've renamed all occurrences of everything, we're going to take all of those definitions and we lift them out of the local. So they are now the global scope. Lift them all the way to. And now that we've lifted all of the definitions out, we are going to scrap the local syntax altogether, pull it out, and leave us with just the body expression from the local at the global scope, or whatever scope you're in. One step does all of that. So to see an example of it actually in use, so here we have our triangle area function from the slide before, and our arguments are 3, 4, and 5. Now traditionally, that we are going to take those arguments, which are A, B, and C, and we're going to in a single step perform all of those substitutions. So everywhere there's an A, B, and a C, we're going to still substitute those all in. Then in the next step, I need to deal with that local. So I've renamed S47 because why would you name a variable S47? And I've lifted it out to the global scope. I've replaced all occurrences of S in the body with S47. I've dropped the local syntax, so now I just have S47 definition and the body expression. One step did all of that. And now I actually evaluate it. So I would start, of course, by evaluating S47. And then after I've evaluated S47, then I would actually perform the evaluation on the body expression. Now you might be thinking, well, that's actually not that bad. This actually breaks a rule that we had before. And the rule that it breaks is the function substitution rule. So here's the problem. If the name of one of the things you defined in the local overlaps with one of the function's arguments, then in the function substitution step, which says, as so long as everything is a value, replace them all into the body of the function, you can't do that in the presence of a local if the names overlap. So if you have an argument x and you have also defined x in the local, then we have to change the function substitution rule. So we can only, for doing the function substitution, only substitute the arguments whose names don't overlap with something in the local. So if x is an argument and x is defined in the local, do not substitute argument x into the body. because x has a more precise scope in the local, and we want to use that one later. So you've got to modify that just a teeny bit. All right. Maybe next class we'll do an actual stepping problem with it. All right. So, why? What is the big why for all of this? The biggest things that you should take away from the why of local is encapsulation and efficiency. So encapsulation, it's going to let us hide all of those helper functions. Helper functions that were poorly named, helper functions that really we didn't want our user to see, but were necessary in order to implement this function. We're going to be able to hide them all inside of the actual function itself, which is really cool. And then efficiency is we're going to be able to pre-compute a value and then use it in the body of the function. That's really useful. So we can pre-compute the value, and if we need it n times, we can just use the pre-computed value n times. Great stuff. Other reasons are clarity. You can actually make your code more clear by using locals. And scope, well, that's kind of a weird reason. All right. So in this particular example, what was really nice is that, number one, instead of having two functions, which was kind of weird, we had this wrapper that computed S and then called the actual implementation. It's kind of weird. We've turned this into a much more clear function where inside of the area calculation function, we compute S, and then we use S in the formula. This is a nice encapsulated piece of code, but it's also a lot more clear as to what's going on. Some other things is it gives us the ability to rename things in meaningful ways, but only inside of that local scope. So for example, suppose we wanted to compute the Euclidean distance between two points in 2 space. And so this would be traditionally how we do it. So you take the difference of the x coordinates, and then you take the square difference of the y coordinates, and you take the square root of the sum of those two differences. Okay, but this is kind of hard to read because you've got this extraction of the x coordinate, extraction of the y. It's weird. If I take the same code and I use a local, you might think that this is more complicated, and in a way it is, but it's also more readable because what I've done is I've created a constant for the difference in x coordinates, and I've called it delta x, which delta usually means a difference. And then for computing the difference in the y coordinates, I've made another local constant for delta y, and then I use those nicely named local constants that are pre-computed in the formula, and now the actual equation is much tidier and more readable, and it's a little bit nicer. So local can be used to clarify things. Can be. I mean, if you use local badly, it's going to look ugly, but you can use local to make things more clear. Now, really, one of the powers of local is this efficiency thing. So, taking you back in time to when we were looking at recursion on a list, particularly cumulative recursion, we wanted to show you the reason we have a cumulative recursion is for functions like computing the max of a list. If without a cumulative recursion, most people give the following solution for getting the max. If the rest of the list is empty, then the first of the list is the max. Otherwise, we check if the first of the list is bigger than everything in the biggest element in the rest of the list, and if it is, we produce it, and if it's not, we compute the max on the rest of the list. And the problem with this implementation, even though we were able to do better with a helper, the problem with this function is that the efficiency of it, the runtime, is exponential. It's big O of 2 to the n, because for each recursive call, we make 2. That's really bad. Yes, there are worse runtimes, but this is really bad. And you might be thinking, it's not that bad. But if n is 1,000,000, there's a big difference between big O of 1,000,000 and 2 to the power of a million. Like, it's an astronomical difference between the two. So, without really changing much of what we've done, but by adding a local, I can actually take this back down to linear time. So what I'm going to do is, so if the rest of the list is empty, notate. Otherwise, I'm going to create a local that defines the maximum of the rest of the list as being a call to max on the rest of the list. I'm pre-computing a single time the maximum of the rest of the list. And then once I've computed that result, I use it in the body of the local, and I check, is the first of the list bigger than the pre-computed rest? If so, produce first. Otherwise, produce the pre-computed value. We take it from 2 to the power of n to n, all by using a local, just to store that pre-computed value. That's a very powerful thing. Yep. Can you use local on assignment 6? No. Yep. And if memory serves me, I don't think you can use it on assignment 7, but you are required to use it on assignment 8. Yeah. Pardon? I will go back. Yes. It's a typo. It should be max list 3. Yeah. Was that your question as well? Do I have to use local to solve this problem? So no, to do the maximum of a list in linear time, I don't have to use local, but the solution on the previous page wouldn't work for that. So we would have to use a helper or a cumulative recursion. You're required to use local on assignment 8. You're not allowed to use it on 6. Yes. All right. So I want to show you one more then. So another thing that we did is I want to not just determine if an item exists in a binary tree, not a binary search tree, a binary tree. I want to know if the item does exist, what path did I take through the tree? So our function before, so we're going to produce a list that is the path to the item. If we find the item, we produce empty because that's base case. If we don't find the item and we're out of the tree, then we produce false. Otherwise, we need to search the left subtree for the item. And if it's in the left subtree, I cons left onto the result of searching for the item in the left subtree. And if it's not in the left subtree, then I'm going to check if it's in the right subtree. And if it's in the right subtree, then I cons right onto the result of searching for the item in the right subtree. The problem here again is this is an exponential function because we're calling BT search path on the left once and then twice for each recursive call. So this is particularly ugly. We can actually simplify this down using a local. Or, you know, the solution we did give you, by the way, was using a helper function. So this was the helper function solution. Yeah, here's my problem. Why I want to use a local is this choose path. What meaning does choose path have in the global scope? None. It only has meaning inside of this function here. So let's use a local and stuff it inside. So instead of stuffing that function inside, what I'm going to do is I'm going to, just like with max, I'm going to pre-compute the result of looking for the item down the left subtree and computing the result for looking for the item down the right subtree. So I look for the results, and then I just compare them. And I take it down to linear time. All right, I will leave it there for today. And hopefully you'll have your midterm grades very, very shortly. They're out. I don't hear any screams of terror, so that's good.